Hello. We are studying Calculus Early Transcendentals by James Stewart, and we are on the topic of derivatives and identifying all the techniques of differentiation. And this is section 3.4, which covers the ever important chain rule. For those in the crowd who would like to study mathematics, I highly encourage you to read the proof of the chain rule in the textbook or in any other calculus text you might have. It's a very rigorous one that definitely starts with the limit definition of the derivative. So I refer you to that proof, and in the interest of time here, I would like to go over how to implement the chain rule. So what is the chain rule and when do we want to use it? We want to find a derivative. When we are looking at a function that is a composition of functions, we can consider, or we can use the chain rule. So let's read the definition of the chain rule. It says if g is differentiable at x and f is differentiable at g of x, then the composite function f composed of g is differentiable at x, and that derivative is given by the following product. And here's our product. And it would be, if we've got the f of g of x, your f becomes your outside function. And notice that the product, or the derivative here, is going to be the derivative of the outside. We're going to evaluate that derivative at the inside function, but then we're going to multiply by the derivative of the inside function. Okay. If you want to look at that in Leibniz notation, if y is equal to f of u and u is equal to g of x are both differentiable functions, then your composition is differentiable at x, and dy dx is going to equal the derivative of y with respect to u, but then we're going to multiply by the derivative of u with respect to x. This is our derivative of the inside. And this is our derivative evaluated at the inside. Okay, so let's use the chain rule and various examples. So before, in part A here, if we wanted to take the derivative without using the chain rule, we would first expand 1 plus 3x squared. That would be 1 plus 3x times 1 plus 3x. We would distribute the terms and then take the derivative term by term, and that would be just fine. But in this case, we're going to keep it as a composition of functions, and we're going to use the chain rule. So I recognize that the outside function is x squared. So when I go to take the derivative, I'm going to take the derivative of the outside, and the derivative of the outside is going to be 2 to the first power, right? And now I'm going to evaluate at the inside, which is 1 plus 3x, but now I'm going to multiply by the derivative of the inside, and the derivative of the inside is 0 plus 3, or just 3. So cleaning it up, we would have that y prime, since this is all multiplied, we want to move our coefficients to the front, and 2 times 3 is 6, and it's just going to be times 1 plus 3x. And that's our first example of the chain rule. In the second example, I might first, instead of employing the quotient rule, I think the power rule is much easier to use than actually going through the motions of applying the quotient rule. So I'm going to use some exponent rules, and I'm going to rename this, or rewrite this equation as x minus 3 secant x to the minus 5, right? And now I see that the outside function is x to the minus 5. And now I'm going to take my derivative, and it's going to be the derivative of the outside, which we would take our exponent down and then subtract 1, and minus 5 minus 1 is minus 6. We will evaluate at the inside, and then we want to multiply by the derivative of the inside. and the derivative of the inside is 1 minus 3 secant x tangent x, right? Because the derivative of x is 1, and the derivative of secant is secant tangent. So now cleaning things up, I'm going to take my negative exponent and put it back into the denominator, and I'm going to rewrite this as minus 5 times 1 minus 3 secant x tangent x all over x minus 3 secant x to the 6th power. Good. And in this third example, I will write a little divider here. I have e to the negative 2t and then another term plus 1. So we're going to be using the algebra of derivatives. The derivative of a sum is the sum of the derivatives, but we also see that one of the terms is a composition of functions. So I see an outside function of e to the minus 2t, right? And so my y prime, and I'm just going to take term by term derivatives. So the first term is a composition, and I'm going to say, what's the derivative of the outside function? E. But then I'm going to evaluate at the inside, but then times the derivative of the inside. And the derivative of the inside is minus 2. And now my second term is plus 1, and the derivative of 1 is 0. So cleaning this up, we get y prime. We're going to put our coefficients in the front, so it'll be minus 2, and we have e to the minus 2t. And we don't need to add our plus 0 because it's just nothing to add, right? All right. And we have the sign of alpha x. Whenever we have alpha, beta, gamma, or a, b, c, we know that those are fixed numbers like 3. They're constants. So in this example, y equal to sine of ax. What is our outside function? Our outside function is sine. And so when we take our derivative, what is the derivative of sine? Cosine. We're going to evaluate at the inside, but then times the derivative of the inside, and that's going to be alpha. And so cleaning things up, we see that y prime is alpha times cosine of alpha x. So it is important to recognize a composition of functions versus a product of functions, okay? And this one's an interesting one. I see a composition of a composition. And so whenever we have a composition of a composition, we still need to do the chain rule, right? So if I just use different colors here, I know that the ultimate outside function is cosine, and then it's going to have an inside function which is its own composition of cosine, right? And so we want to, just as an example or as a rule, if we've got y equal to f of g of h of x, then our y prime is going to be the derivative of the outside evaluated at the inside but then times the derivative of the inside, and the derivative of the inside is going to be the derivative of that outside, outside, inside, inside, outside, whatever, evaluated at that inside, but then times the derivative of the inside, right? So we want to do a chain, chain, chain. That is our rule here. That you'll want to remember. Oh, I'll put that in there. Okay, so in taking that, my f of x here, this is going to be the derivative of the outside is minus sine. I'm going to evaluate it at the inside, but then I'm going to multiply by the derivative of the inside, and the derivative of the inside is going to be another chain rule. And what's the derivative of cosine? Minus sine. I'm going to evaluate it at cosine, but then I'm going to multiply by the derivative of the inside, and the derivative of cosine is minus sine x. Okay. I'm going to clean things up. I've got 1 minus, 2 minus, 3 minus, so this is going to be my y prime here, or f prime, is going to be a negative sine of cosine x times sine of cosine x times sine x. Good. And that's going to be our slope function. We have, this is our point over here. It says find the equation of the line tangent to this curve at the point pi over 2 comma 1. This is our x1, y1. And so if I'm going to evaluate my slope function at pi over 2 equal to x, we have y prime is minus sine of cosine pi over 2 times sine of cosine pi over 2 times sine of pi over 2. Good. And if I just start from the very beginning, or the very inside, I'm going to get minus sine times the cosine, and cosine of pi over 2 is 0. Sine of the cosine of pi over 2, cosine of pi over 2 again is still 0, and sine of pi over 2 is 1. Minus sine, cosine of 0 is 1, sine of 0 is 0, and anything times 0 is going to be 0. So my y prime evaluated at pi over 2 is going to be 0, and that is going to be my slope. So I have a horizontal tangent there, right? And if I did just go ahead and put my equation, typically you would put your equation together using the point and the slope. So you're using the point slope form, which is y minus y1 equal to m times x minus x1. And I have my values of x1 and y1 up here. So I just plug them in, and I have my m, and I plug that in as well. And what do I get? So my y1 is 1, my m is 0, and my x is pi over 2. We do have that anything times 0 is 0, and so we end up with just y equal to 1 is our horizontal tangent. Good? All right. Here in this example, it says find all values where f of t is equal to e to the sine squared t, and find all values where this function has a horizontal tangent. So remember, I mentioned just above, horizontal tangents mean the slope is equal to 0, right? So that means we want to find values t where f prime of t is equal to 0. Good? And so first we have to find our derivative, and our derivative here is a composition of functions, but it's actually a composition of a composition, because our f of t is equal to e, and if I rewrite sine squared as sine squared, a sine of t squared, my outside function is really e to the x, right? And what is the derivative of e to the x? E to the x, or e to the t. I'm going to evaluate at sine t squared, but then I'm going to multiply by, and that's not going to remain in the exponent. You're multiplying the entire function by the derivative of the inside. And the derivative of the inside has its own inside-outside. Our outside function is the square, or x squared, t squared. So it's going to be 2, and it's going to be evaluated at the inside, but then times the derivative of the inside. And the derivative of the inside is cosine t. So cleaning things up again, we have got 2 sine t cosine t times e to the sine squared t. Okay, and we want that to equal 0, right? When does a product equal 0? When one of the factors equals 0. So this is going to equal 0 when sine t is equal to 0, cosine t is equal to 0, or e to the sine squared t is equal to 0. Your exponential function is never 0. Right? That gets really close to 0, but it's never going to be 0. But sine t and cosine t in your range of values is going to give you 0 when t is equal to 0, pi, 2 pi, 3 pi, 4 pi, 5 pi. So when t is equal to k times pi, where k is an integer. It can be a positive or negative integer, because negative pi would have sine pi is equal to 0. So that's one answer. And what other values of t? And when cosine t is equal to 0, then t should equal pi over 2. That's 1 pi over 2, 3 pi over 2, and then we jump again to 5 pi over 2, 7 pi over 2. So it's going to be t is going to equal, and we want to represent an odd number. So the usual we do is we do plus or minus 1. 2k, which is an even integer, and if we add 1 pi, where k is an integer. And those are all the values of t for this function that will have a horizontal tangent. Good. All right, sometimes these things get a little wacky because we've got complicated, we're going to be doing the chain rule with other complicated processes like the quotient rule or the product rule. So sometimes it's a double chain like what we just did with a composition of a composition. Just keep going with the chain. And in these examples, we might need to employ the quotient rule. So this is a function that also is the same as 2x plus 1 over x plus 5 to the 1/2, right? And so what is my outside function? My outside function is the square root. And so when I take that derivative, I'm going to take 1/2, and then I'm going to go to the minus 1/2 because I take the exponent down in the power rule. If I've got a variable to a number, I use the power rule. I take the exponent down, and then I subtract 1 from that exponent. I'm going to evaluate at the inside. But now I have to multiply by the derivative of the inside. And the derivative of the inside needs to use the quotient rule. And remember what the quotient rule is. If I've got y equal to f over g, y prime is the derivative of the top times the bottom minus the top times the derivative of the bottom over the bottom squared. So here I go with that. The derivative of the inside here being the derivative of the top is 2 times the bottom minus the top, and don't forget to subtract the entire top, times the derivative of the bottom, which is 1, all over the bottom squared. Good. I want to clean things up and note that if I want to take that radical, this radical here, if I want to take that to the denominator, it would be a positive, and we can use our radical rules. The radical of root a over b is equal to root a over root b. We also have that if we've got a over b to the minus c, that's going to equal b over a to the positive c. Good. So that's what I'm going to do here. I also note that I've got the 1/2 and I'm multiplying. I can't do that yet because I have to distribute. That's only the 2. So here I go in the simplification. I still have the 1/2. I'm going to write this as x plus 5 to the positive 1/2 over 2x plus 1 to the positive 1/2. I'm going to distribute. This is going to be 2x plus 10. Take away 2x, take away 1 over x plus 5 squared. I now can do some canceling. I know that half of an x plus 5 cancels with x plus 2 x plus 5s to leave x plus 5 to the 1/2 or 3/2. And then I can finally, the 2x and the minus 2x go away, and I end up with 10 minus 1, which is 9. And so my final answer here will be 9 over 2, and I can change that to radical again, 2x plus 1, or I can leave it as it's 1/2 if I want to be consistent with the next one. 2x plus 1 to the 1/2 times x plus 5 to the 3/2. And we want to feel okay with that. It is just a formula. Now it's a slope function, and we are now able to calculate the slope of any point on that function and calculate the equation of a tangent line. Good. I'm going to skip that one for now just to move more questions. Here we have the derivative, or more applications. Here we have the derivative of the exponential function. This is examples might be 2 to the x, 5 to the x. These are all exponential functions where the variable x is in the exponent, so therefore exponential. You would not use the power rule on these. So we can rewrite, because e to the x and the inverse function is ln of x. If we have f of x equal to e to the x, then f inverse of x is going to be the ln of x. And if we know that the composition of inverse functions undoes itself and it just gives you the identity, then we do know that e to the ln of x is a composition of functions, and it's just going to give us x. So e to the ln of 3 would be 3. E to the ln of 2 would be 2. So we can show here that the derivative of the exponential function is going to be a to the x times the ln of a. And this actually should not be here. This is not right. There you go. Where a is bigger than 0. And so the proof is we can write a to the x as e to the ln of a, right? And this here, e to the ln of a, and that's to the x. And we know then that if we're just using x to the a raised to the bth power, that's x to the a times b. So we can rewrite this as e to the x times ln of a, or ln of a times x, right? And now if we use our chain rule, then we've got our outside function is e to the x. And so my y prime is going to be e evaluated at the inside, which is ln of a times x, and then times the derivative of the inside. And the derivative of the inside, if it's something like 5x, it's just going to be 5. So this is just going to be ln of a. And now we can rewrite this back as a to the x times the ln of a. And it does match up. If we had y equal to e to the x, then y prime is going to be e to the x times the ln of e. And that's log base e of e, and we know that that is just going to be e to the x times 1. So it matches up with our derivative of e to the x and our definition of that. So here we just play around with some funky things, or funky functions. So in the first one, in part A, it says find the second derivative. So first let's find the first derivative, because we know that the second derivative is going to be the derivative of the first derivative. And we know that the derivative of a sum is the sum of the derivatives. We have the rule y equal to x to a number, then y prime is going to be take the exponent down and subtract 1. And if we have y equal to a constant, then y prime is equal to 0. And finally, from above, if we have y equal to the exponential function, then y prime is going to be a to the x times the ln of a. So we have all three types in this example. X to the pi is 3.14. Pi is a number. So we're going to say that this is going to equal pi times x to the pi minus 1. The second term is an exponential function. It's a number to the variable x, and so our derivative is going to be pi to the x times the ln of pi. And the last one, pi to the pi, is a number to a number, and that is a constant. So this is going to be 0. Good? And so we do this again, and we're going to take the second derivative, right? And the second derivative, the derivative of a constant times a function, is just the constant times the derivative of that function. So we don't worry about the pi, and we don't have to use the product rule. We just keep that constant. So we have pi times, and our derivative there is going to be pi minus 1 times x to the pi minus 1, which is minus 2. And then in the second one, we are still using the constant times the derivative of the function. And so we've got, what's the derivative here? We've got pi to the x times ln of pi, but then we're still multiplying by that constant. And we don't need to do the derivative of 0. Good. So we can clean things up if we want and just say that this is just equal to pi times pi minus 1 x to the pi minus 2 plus pi to the x times the ln of pi quantity squared. That was kind of fun. Maybe. Hopefully. You just got to make sure that you know what you're looking at and know the difference between the exponential function and the polynomial function or the power function. All right, so lastly, let's do this one. I see that the outside function is going to be 5 to the x, right? And that's exponential. So when I take my y prime, it's going to be 5 to the x times the ln of 5. And now I'm going to evaluate at the inside, but then I'm going to multiply by the derivative of the inside. And the derivative of the inside is 0 minus 4x, so I just have minus 4x. Okay. And to clean things up, we typically put coefficients in the front, followed by algebraic functions, followed by exponential functions, and then trig functions. And so I'm going to put a lot of the coefficients in the front, and I might say that this is equal to, we've got minus 4 times the ln of 5x, right? And then multiply by 5 to the 1 minus 2x squared. And that would be our derivative function. Make sense? Hopefully. And that does it for this section of chain rule. And we will be using the chain rule everywhere you see a composition of functions that are hard to expand or to reevaluate. So if you see a composition of functions, there's no way to algebraically manipulate it to turn it into a product or to turn it into something else. Use the chain rule. Good.